all speak in English because there are some connected people here. So it gives me great pleasure to introduce you to Jeremy and Gregory. We have been working together for quite some years now. First in the scope of the MIT Portfolio projects, and then also in relation to several doctoral students. So it's really a big pleasure to have Jeremy here. Jeremy has been in Coimbra several times, but this was the first time we really had an opportunity to invite him to be a formal call to the university. Unfortunately for the university, it's not the best time because this is the Easter holiday, so I don't have any excuse that we don't have so many people that this is a bad time in terms of people coming. But, so the floor is yours, Jeremy.
Great, great. Thank you very much, Fausto. Yes, I've been coming to Portugal for, I was more involved in the EDM program, MIT Portugal program, as the education coordinator on the MIT side. It's been many years going to, between IST and Minho and Porto, but then it was nice to be able to add a fourth university, particularly even though it wasn't part of the EDM collaborators. It was nice to have a research project that allowed us to collaborate directly, and so it's a pleasure to be coming back here, and also to be talking about some work that we've been doing at MIT, but also had Carla Rodriguez involved in, and so that's why we listed her up there. But this work comes from some research that we're doing at MIT in the context of the Concrete Sustainability Hub. But actually, I come from a research group called the Material Systems Laboratory. And the Material Systems Laboratory, we look at essentially economic and environmental aspects of engineering decisions. So engineers are trained very well how to make technical decisions, but they're not trained so well how to look at those economic and environmental aspects of those decisions. So that's a lot of the work that we do. And that led us to then get involved in doing work like life cycle assessment and life cycle cost analysis, and that led us to then get involved in this Concrete Sustainability Hub. And the interesting thing about the Concrete Sustainability Hub is that actually, there's a lot of research that goes on related to how to reduce the environmental footprint of cement and concrete. But what we're actually trying to do is look beyond that and look at how how's concrete used, and then how do we quantify sustainability performance basically of infrastructure. We've been looking at a lot in terms of pavements and buildings. And so obviously the footprint of the materials that you use are important, but what's often even more important is basically what's the context in which they're used and how is the design and how is it implemented. And so that's kind of the broader scope by which we have this. And there's a lot of other projects we have going on. The one that I'm going to talk to you about today is about essentially life cycle assessment applied to residential buildings. And so, as many of you know, life cycle assessment is this method that's used to quantify the environmental footprint of a product or a process. And one of the things that we found is that it's a costly and time-consuming process. And so the research that we've been doing is in trying to streamline that and using. One of the ways we've been doing it is this technique called probabilistic underspecification. And I'm going to talk about what that is. But there's a significant opportunity, at least what we have in the United States, where there's a lot of estimates about things like the green residential market, which by that I think they mean opportunities for buildings to be built that have a lower environmental footprint. This is an estimate that was done that was basically showing how it's been rising and then potential opportunities for it to grow even further. But I think the key thing that you see there is that it's definitely growing. And what's interesting, the total amount is growing, but also the fraction of the market is growing as well. And in the US, we have lots of open space and lots of opportunity to build new buildings, and so that's what happens quite a bit. The other thing, though, that's interesting combined with that, we did some work trying to understand a little bit about how decisions were made in the building process. And what we did is we did some surveys of architects and asked them about when in the design process are they making decisions about what they're going to be doing with that design. So for example, we asked them, when do you finalize what kind of foundation you're going to use, or what you're going to use for the roof, or fenestrations, it's about windows. when do you make those in terms of these elements of the design process, okay? So you start out with the conceptual design where you have a very rough idea of what it is that you're going to be doing, then move on and gradually adding more and more detail. And what you can see in terms of the survey is, that very few architects actually have a lot of details that they've specified early in the design process. Rather, they are, making final decisions about those late in the design process, right? So the reason why we were asking about this is because, a tool like life cycle assessment should be used to support decisions, okay? And the challenge here is that if decisions are, this is actually when they're considering what to do with those decisions, and then this is when they're actually making them, okay? And what's interesting is that, the further you move along in a design process, the more difficult and costly it is to make changes. So, this is the curves that you see in the context of many different design processes, but obviously your ability to impact the cost and functionality decreases over time. And similarly, the cost of making changes to the design increases over time, okay? But what's interesting, like what we just saw, your traditional design process has a lot of effort in putting those details late in the design process, right? What they're trying to do, maybe some of you are familiar with a BIM process, which is basically a more automated process by which you define what materials are being used. They're trying to get that earlier. But, the easiest place to make changes to the design is early in that process. But here's the issue, is that most of the life cycle assessments are done using detailed designs that happen. As a matter of fact, I would argue that when it comes to buildings, most of the life cycle assessments you see are really done on final designed buildings. Yeah. And the interesting thing is that that's when you have very little opportunities to actually make changes to the design, right? So essentially right now, a lot of times those life cycle assessments are done basically to justify decisions that have already been made, right? Or, and that's, to be honest, that's a common evolution we've seen in life cycle assessment, that originally you do it just to kind of demonstrate the process, and ultimately moving it to a place where you can support decisions is more challenging. So what we're trying to do in our research is basically align the life cycle assessment with the information that's available earlier in the design process. And that's a big motivation for us to try to do that streamlining to make it easier to be used early when you have less information available, okay? The other big thing I think that's happening in life cycle assessment is that there's this tension between cost and credibility, okay? So the cost part is that obviously the more detailed a life cycle assessment you want to do, the more expensive it is. And expensive, I mean in terms of just time, but also a lot of times it's being done by consultants, and so time is money. So the cost can just be in terms of time, but it can also be in terms of the dollars or euros that you're spending to get it done. On the other hand, the stakes for life cycle assessment have never been higher. That is, now they're being used in policy decisions. The private enterprise is also starting to use life cycle assessments as part of their business practices. Some of you may have heard of environmental product declarations, which is kind of like a nutrition label for a material or a product that tells you what's the environmental footprint of that, right? So there's starting to be a much more public face where you need that increased credibility, right? And often what happens is that you get that increased credibility by putting more money into the process, right? So clearly, if we want to be able to scale this up, then that's often going to be associated with more cost, right? So when we look at how a standard building life cycle assessment is done, it usually essentially has this high cost and high credibility approach, right? Generally what you do is you use what we call a bill of activities, which is like a bill of materials, which says, here's the amount of mass that is in the building, but it can also include things like how much transportation there is, how much electricity is used. So that bill of activities, it kind of says, here's the inventory that's going to be used. We multiply that times impact factors like environmental impact for different types of materials, and then we ultimately get are life cycle environmental impacts. Okay, so there's a lot of data that's involved. It takes a lot of time. But obviously, most people who design products don't have information in terms of what we need for a life cycle assessment, right? They don't, you ask them, in fact, we've actually found this in work we've done with electronics. If you ask a company that sells a product like Dell, what is that made out of? They usually can't tell you, and that's because all the components are provided to them by suppliers, right? And they don't specify what the materials are, they specify functionality, right? So doing a life cycle assessment for a company that outsources everything can be very difficult. So usually what you get is some type of product description that says, if we use the laptop example, this is the size of the screen, this is the hard drive capability and things like that. So there's even a process that's involved in basically, getting the description of that into that bill of activities. And that's where a lot of the cost and effort is involved. And that's what can make it difficult to scale up and can also make it difficult to support early design decisions when you don't have all that information available, okay? So what we've developed is an alternative that we call the building attribute to impact algorithm. And what we're trying to do is maintain that same credibility, but reduce the cost, okay? And so that's what we call it a streamlined method because we're trying to make it be faster and more efficient, but maintain that credibility, okay? And it's still gonna have the same basic elements of taking a product description and then generating that activities and multiplying it times impact factors to get impacts. But there's a couple key elements that I'm going to tell you about that allow us to make it more streamlined, okay? One is what we call attribute to activity models, okay? And essentially what we want to be able to do is basically have a quick way for designers to say, here are the attributes of my product, okay? And then we use our model to be able to generate the bill of activities, rather than asking a designer to tell us how much mass is in the building, okay? So we have a couple different ways to map the attributes to the amount of materials and processes and energy inputs that go into there, okay? Another thing that we use is an approach we call underspecification. And the key element of this is that we have low fidelity, high uncertainty data. And low fidelity, what I mean is that it's not very specific. Basically, you're just giving a rough approximation. Rather than saying exactly what kind of wood this is, I just say, this is just wood. I don't know if it's soft timber, hard timber, whatever. So low fidelity kind of means that I'm not being very specific. But I am going to quantify the uncertainty associated with it, okay? And then the last thing is a probabilistic triage. And triage basically means you're trying to figure out what's most important. And I'm going to use that by leveraging the uncertainty that I've already specified in here. And the key thing there is I'm going to identify only what's the important data that I need with limited effort, okay? And so this allows us, this is another key component of the Streamline, because it basically says there's a lot of data that you can collect, but I only want you to collect the data that's most important, okay? So I'm going to go through each one of those things, but first what I want to do is just give you a high-level overview of what's kind of the approach about how you use all those things, okay? And what we're trying to do is to be able to gain insights early in the design process, but with minimal data, okay? So you start out where the user is going to put input into the model that's underspecified. And as I said, I'll get into that a little bit, but basically they're just very generic. Here's a rough approximation of what I'm going to be using in the building, okay? Then what you do is you run the model, and it's a probabilistic model, so it includes uncertainty. Another key element that's different than a lot of life cycle assessment approaches is that it includes an analysis of the energy consumed in the building and the embodied impacts in the building. And by embodied impacts, I mean the impact associated with the materials and the construction of the building itself. And that's also something that you don't usually see in life cycle assessments, okay? What we then do is we quantify an environmental impact, and here's an example with the global warming impact, and we have that for the embodied phase and the use phase, and notice that it has a range of uncertainty associated with it, okay? So that's one thing we get. The other thing that we get is basically what are the parameters that went into it, what are the ones that had the biggest impact on the results, okay? So this is the triage part. It basically says, if you want to lower that uncertainty, what you're going to do is basically try to go after these data and make them more specific, or just get better data on So then you can refine these top ones and then run them again and keep the process going until basically you've reached a level of resolution that supports your decision. So at a high level, this is what it is. What I'm going to do now is spend some time going into each of these to explain them a bit more. But a few key points that I want to make now that I hope I get across about what are some of the benefits of this approach. One thing is that the design attributes are inputs, okay? I realize it seems kind of like something that should be obvious, but in life cycle assessment, that's usually not the case. Is that basically what we're doing is trying to say, have a designer tell us broadly about the building, then we'll do the work and translate that into the inputs you need for a life cycle assessment. The other thing is that we have a combined energy and embodied analysis. Now, I really can't emphasize enough in the building world how much these two worlds are considered separate. You have people who do energy analyses and you have people who do analyses about the embodied portion. And when it really comes to, as you'll see in many of our examples, the use phase obviously dominates, but decisions you make about materials have impacts on that. And so we think it's really important to be able to combine both of those together. The other thing that we do is we provide feedback on what are the key parameters, and you don't usually see that in a life cycle assessment either, right? But we're able to provide that because of the probabilistic nature of the analysis. Oops. Another thing, the user only has to specify the details that really are necessary in order to get the answer they're looking for. Everything else they can just keep generic. You don't have to be detailed about everything. And lastly, we quantify uncertainty, and we think that particularly when it comes to life cycle assessment, this quantification of uncertainty is really important. So, all right. So what I'm going to do is basically go through each one of these to describe a little bit more, kind of what's under the hood. So I'm going to start with this attribute to activity modeling, right? So when I'm talking about an activity, once again, it's basically going to be this bill of activities, and you'll see what I mean by attributes. So we have a couple different ways that we estimate bill of activities, but essentially what we do is the kind of attributes that we're asking in architecture, the designer to specify, tell me about the rough geometry of the building, what are you thinking about in terms of wall systems, attic and roof, the things that an architect would already be specifying. Then we have an energy activity or attribute to activity model and one for materials as well. And essentially what we do is we take all those attributes and then we have a model that we use to then calculate what's the energy consumption of the building, okay? Then we have a different one where we basically use those same attributes to specify what are the materials that are in the building. So, the key thing is we want to be able to do this in an efficient manner, okay? So the use phase attribute to activity model, that's probably the one that's the most tricky usually to specify, because a lot of times in order to get energy consumption information, it requires a lot of simulations. And so essentially what we do is we basically, to develop this model, we use this program called Energy Plus, which is common in the US, developed by US Department of Energy. And it's a simulation tool that you use. What we did is basically we generated thousands of different designs using that, then ran Energy Plus simulations, and then predicted energy consumption for each one. What we did is we developed basically a regression model that basically said out of all those thousands of runs, we can then have a statistical model we use to connect those attributes to the output. So it's not as perfect a simulation as what you have if you were to use the actual model, but developing that regression model means it's very fast. It's almost instantaneous. And so when we're going to be using our tool, that's much more efficient. When it comes to the materials, attribute to activity model, it's a bit more straightforward. We basically are just calculating the areas of assemblies. So if you tell us this kind of geometry, what are aspect ratios, roof pitch, things like that, we just use that to kind of calculate assembly areas. So it's a bit more straightforward. It still requires some calculations, but that is how that works. Okay, moving on next to underspecification. So this underspecification essentially works on this premise, as I said, of low fidelity, high uncertainty data, okay? And essentially what we've done is set up a hierarchical data structure. And what we do is we basically say, let's categorize materials in a few different ways. So this is showing one such structure where essentially we've categorized them into material classes, right? In level 1, 2, 3, 4, and 5. So the most broad level would be just metals. Let's just call something a metal, right? And you can imagine that for any kind of product, you might say, I know I'm going to use a metal. Maybe within that, you would obviously break it down to ferrous metals. You could have more that we're not showing here that would be non-ferrous metals. But within that ferrous metals, you could then say steel and iron, then more specific categories. And then finally, you might even have like specific data sets of these that you're interested in from, say, EcoInvent or Gabby. And the key issue here, though, is that what we do is we capture that range of uncertainty across all these categories. So if you were measuring life cycle environmental impact, as you can imagine, this category would have a very wide range of uncertainty, whereas the uncertainty here would be much less, right? So here, if you go in this direction, you're getting increased specificity, but also we're saying more broadly a higher cost, right? It might take you more time to figure out which exactly one of these that you're going to need, and so that's the trade-off here. What the idea for what we're trying to do is basically to say that if you start out by being more generic, you don't need to spend the time and effort to go into this level of detail for everything, right? There's likely going to be a lot of things that you don't need to do that for. But regardless of what you choose, we're going to capture that uncertainty, and so that's what we're trying to do there. And we've applied that like I can share a paper with you that was published a few years ago by some of my colleagues kind of outlining this whole approach. We've applied that to other industries, including the electronics industry. Now what we've been doing is applying it to the buildings industry. And so how we define that for buildings, first of all, we say you can underspecify the definition of what it is that you're talking about for a building, right? So you don't have to tell me exactly the size of the house. You can just give me a range. You don't have to tell me exactly how many windows you're talking about. Just give me a range. You can underspecify those attributes. Similarly, when it comes to specific assemblies within there, you don't have to tell me exactly what kind of wall system. You can just give me a rough approximation of the wall system or what kind of roof. And then when it comes to the specific materials you're using, similarly, you don't have to tell me exactly which materials are in your wall system. Just say it's just some kind of insulation. So that's how the underspecification works there. Just giving a few more examples. At the building level, we're essentially saying how much of which assemblies are at the assembly level, then at the material level of which specific things. So we've set up categories of L1 to L4, and then users will then specify or allow, basically just have it be completely underspecified, which means they just choose the most generic category of this L1. And then a key thing here is that these building level attributes are independent of the assembly and material level attribute specification. So remember, because this is basically saying how much of something that you're using, and this is exactly of which type. So you could say, I want to choose a very specific wall, but I don't know exactly what size the wall is going to be. So those things are independent. So here are some examples. So like when it comes to the geometry of the house, building level 1, which would be the most generic, you can just say any size house. And at least with the US, we have data on kind of what are the main ranges of the size of houses. The next one would just be, I just know I want a medium-sized house, right? And then it could be on the smaller size, and then the most specific would be, here's exactly the size of the house, right? We can do the same thing with about the building systems, like the heating and cooling systems. In particular, air leakage has a big impact on how much energy consumption you're using. So you could say any level, you could be kind of generic and just saying, I know it's just going to be low air leakage, or you can say a very specific amount. We can do similar things with the exterior walls then. There are different elements that you define of the walls. Within the wall core, the generic one would be any kind of wall system. And then these would be more specific. Here's insulated concrete forms is what this one is, which is this right here, where they use insulation on either side and then concrete goes in the middle. Within that rigid insulation part, then basically you could specify, here's exactly what kind, I just know I want rigid insulation, or I can get more and more specific. So hopefully that kind of gives you the idea. We have other examples here. In the building level, you can do window to wall ratios, roof pitch, or overhang length for many different options. When it comes to assembly level attributes, there's all sorts of types of exterior walls, insulated concrete forms, structural insulated panels, concrete masonry units, and so within this insulated concrete forms, there are different sizes you can use, different types of insulation, so it's a lot of combinations. This is showing actually a snapshot of how we've implemented it in a spreadsheet, but basically then once you choose some of these groups, then you can go in and actually choose specifically what kinds of materials you want. Or as I said, you can also just leave it very generic and just say, I don't know. So those are some of the different options. All right, so last but not least, probabilistic triage. And it's a little bit of a fancy word for essentially a sensitivity analysis, but what we do, the reason that we want to do it is to be able to identify what are the influential attributes that are going to be in this model, okay? And so we use a sensitivity analysis. The technique we specifically use is these Spearman rank correlation coefficients, but they essentially provide an approximation of the contribution to variance. So when you do an analysis, you don't just get the uncertainty, you also then get a ranking of which specific attributes are going to contribute the most. And like I said, this is also something that you don't normally get from a life cycle assessment. The key thing about contribution to variance, it's not just contribution to the total, which you can get from a traditional life cycle assessment, it's contribution to the variance, like how much is this contributing to the uncertainty. So that's going to be a combination of how much does it contribute to the total, but also how much variation is there in it. And so the attributes that we have here, for example, would be the kind of key things that you would get from an output that you would then say, I'm going to triage this and say I'm going to ignore anything that's not even on this list and not really worry about specifying that, but I am going to go after these top elements that are here. So, all right, so let's put it back together. This is our overall approach again, like I said, where you have a user inputs information, you run that model, get results, look at the attributes, and then perhaps refine it. So let me give you some examples of how that looks. But basically, you start out with building level inputs, assembly level inputs, and material level inputs, and here are some examples. It goes into the model, and then from that, you get the total life cycle environmental impact, but you also get a breakdown of what's the energy use and what are the bill of materials, and then you get a sensitivity analysis out of that as well. The way that the probabilistic model works, what we do is we take all that input and then we run a whole bunch of Monte Carlo simulations, okay? For us, usually it's about 5,000 trials. In our spreadsheet model, that just takes like a few minutes, so it's not too bad. But keep in mind, we have a variety of different sources of uncertainty. We have uncertainty because of the underspecification in those attributes. So when we do that underspecification, that means we have a range of different impacts, but we're quantifying that uncertainty. We also have uncertainty in the amounts, like basically what's the exact thickness of each layer as well. So there's uncertainty there. And then what we do is basically, the way that we manifest that underspecification is that we essentially take random selections of which data set that you're going to use. And one of the things I like about this is that we spend a lot of time talking about which kind of data set is the best, right? And we're using a whole bunch. We're using EcoInvent, ThinkStep, the US Life Cycle Inventory. We don't really care. We'll take them all. And because a lot of times it just doesn't matter, right? Even for some of them where you see significant ranges, it doesn't. But there will be times where it does, and that's where we can get that. And then there's some other properties where we have ranges in. The other thing that's nice about doing a probabilistic model is that you're able to get that sensitivity analysis that allows us to do the triage. So how does this work? So for example, this parameter here is a window to wall ratio. And let's say it's unspecified, so we just have a significant range. So when the Monte Carlo analyses take place, we just have a uniform distribution. We don't have information on what's any weighting we can use. We can just use a uniform distribution, and a whole bunch of trials are run, and we get a distribution. If you decide that you want to specify that further, let's say you knew you wanted a low value, okay? We can run it again, and likely what will happen is we'll get a narrower distribution on our results. So that's kind of the idea behind what we're doing. So as I mentioned, the kind of results that you would get would be, here's, if you do it completely unspecified, then you get a certain amount of embodied impact, the use phase, and the total, but you get these attributes. Then you can spend more time specifying these three parameters that are mostly about insulation and window types, which is, I would imagine, given how dominant the use phase is, those are parameters that are going to impact that. Then you can run it again, and you see you get a lower environmental impact compared to what you have there. And now you have other parameters that are the top rankings there. So depending on what you're interested in, you can run it again. So let me give you an example here that basically shows just a house that's, we choose an analysis period of 60 years in Chicago. Some things you can specify. Let's say you're a designer and you already know, I'm going to do a house that's of this size. You know you want 3 bedrooms, you know you want 2 stories, and I think those are common things that a designer would know. But on the other hand, you might not know yet what material you're going to be using in the walls, or maybe specifically what kind of HVAC equipment, or heating, ventilation, air conditioning equipment you're going to use. So you run it for the first time, you get these kind of results in terms of global warming potential here, and you get this for an embodied use phase and a total. And as we said, what it tells you is, in this case again, specifying the insulation in the attic and the insulation in the roof deck and the windows. Those are key elements. So let's say then we decide, I'm going to use this specific type of insulation in the attic. I'm actually going to choose no roof insulation, and then these specific types of windows. So I go to the next level of specification for those, and then with run 2, now I've specified those, you can see the uncertainty goes down quite a bit. And now I have different parameters that are the most influential. And so the next thing I'm going to do is basically, I found that on the exterior wall, specifically what I chose for that core material has the biggest impact. And so the next thing I specify is I want to look at a couple different options. One is using these insulated concrete forms, and the other one is using wood studs. So what I can see with that here are 2 runs, one where I've done it with insulated concrete forms, and one where I've done it with the wood studs. And it's actually just not that big of a difference. And also what's interesting, you don't get nearly the same amount of reduction in uncertainty as you do with that first phase where you specified those first few parameters. So now we can see the total global warming potential across all those different runs, where, as I said, uncertainty dropped quite a bit for here, but then from here to here, from run 2 to these runs 3 is not quite so much, but still there's definitely some. You can compare these 2 alternatives, and that can hopefully support some of your decisions. So once again, just to wrap up, I want to emphasize these, what are some of these, the benefits of the approach. You get these building design attributes as the inputs. You have this combined energy and embodied analysis. You get the feedback on what are the key parameters. You only need to specify the details when they're necessary. And then lastly, we get that uncertainty quantified for the environmental impact. So we think this is a tool that can be used to guide those early design decisions when you don't have all that information available, and it can be used in those early design stages and can capture uncertainty. And I think a key thing is that basically there are certain things that you just don't need to specify in terms of that overall environmental impact, and that can be something very useful. So we have a tool developed for residential. What we're doing now is making sure that we have all the data we need for all the life cycle stages, like I didn't talk about end of life there, or some of the construction impacts, and so we're adding those. What we're also doing then is trying to analyze a wide range of scenarios to really figure out, when we look at all these different scenarios for different types of buildings in different locations, what are the things that keep coming up? What are the things that really matter and can drive that? Trying to add in a simultaneous cost analysis. which is actually an interesting thing Carla Art has already done for her model, so she's way ahead of us in terms of that attribute. But the next thing we also want to do is basically scale this up to other types of buildings, some multifamily buildings, and then also to commercial buildings as well. So that's all I had. If you have, I'm glad to answer questions now. We also have some other information on our website. Right, you can always send me an email as well. So.
Okay, we have time for questions. Who wants to start?
Hi, nice to meet you, and thank you for your presentation.
You're welcome.
It's a very interesting work.
Good.
Regarding that you presented the model that try to incorporate different levels of uncertainty and of underspecification, what do you think about using input-output analysis instead of process-based analysis? Because it seems that you are using process-based, right?
Yes.
From a pavement.
Yeah.
But as you go far away to uncertain and unspecified categories like metals, and they are close to an input-output analysis. It seems to me, I'm not very in the input-output analysis, but I'm just reading some papers about that and trying to do a small exercise to compare process-based to input-output analysis. So I would like to have your opinion.
Sure. No, it's an excellent idea, and I think actually input-output is something that can really be something that you could use in a similar type of approach here, particularly when you're just being generic and don't need to be more specific. I think one of the challenges, obviously, with incorporating that is that your inputs for an input-output analysis are different than they are for a process-based approach, right? There you need to be specifying what are your inputs in terms of monetary inputs, right? So here we're asking designers to specify that in terms of, just attributes of the building. So we could, I mentioned those attribute to activity models. We could essentially set one up to basically say, tell us about those attributes and then turn them into costs. And what's interesting, when we do a simultaneously cost analysis, it might be a type of thing that we can use that component to then add it into an input-output type framework. So I think it's set up for it. We just haven't done that extra step to actually generate the inputs in terms of costs. What a lot of people do, and maybe you've read about as well, is a hybrid approach, which is to use the input-output data for a lot of the background type processes, and that might be also an interesting thing to be able to set up. So I think the short answer is the potential is definitely there and could easily be done. We haven't done it yet. So.
Because at least from reviewing some studies, it seems that embodied energy gets really higher when you consider an input-output analysis.
Yeah.
And I'm a little bit curious about these unveiled impacts that are so many and so indirect to trace back, but they are there. They are embodied in the constructions and in the companies that work for the construction sector. One interesting thing that the folks who do the input-output have realized the limitation is that they, the stuff that they've done is really only focused on essentially materials or processes, but they haven't really had any use phase elements to the work that they do. And they have some research the folks at Carnegie Mellon have some research that's going to be coming out. They have been working on that for certain types of appliances. So, because I think that would also be something that obviously the use phase component here is really important. There is electricity that's in there and natural gas consumption. So it could be that based on kind of the way that we've done these attribute to activity models, we could tie that together with what they already have on electricity and those databases. But we'd once again need a way to kind of translate those into cost. The other thing that's tricky, and I've talked a lot with the Carnegie Mellon folks about this, is capturing the uncertainty in the input-output database is difficult. They know that and have been trying to work with it for a while. And actually, there's also some new research, I think, that's going to be coming out where they've been trying to do that. But that's obviously such an important part of what we're doing that we would need to add some kind of element into that as well. But I think it's
as you said, it is something that's well suited to what what it is that we're trying to do, and I think it would be interesting to think about some ways to add more in. So.
My question is about BIM, because we talked about it, and I think it's quite interesting because I'm a BIM user.
I say good.
I'm an architect, and I'm very lazy to do it while I'm modeling. And I think it could be really interesting, and because BIM has a level of detail also, it has that uncertainty, and you could link it to your work.
Yeah.
How do you see it? How could we do it?
Yeah.
Because it's something that interests me quite
Yeah. I think we obviously haven't gotten to the point where we've done that. We have been talking with some folks in Canada from the CIRE group, who you may or may not know, and I think they have an approach that they're developing where they're much further along. So we've talked with them about possibly collaborating on that, because essentially it once again comes down to the LCA part. You obviously need some kind of quantities of materials, and so that BIM is very much well set up to be able to do that. I mean, there is, keep in mind, there is a software program that's already out that's called Tally. I'm not sure if you've heard about it, but there's a program that's called Tally that is an add-in to Revit. And Revit, have you heard of Revit? Okay, good. So you can look up Tally, Tally, and essentially how that is set up is basically to take any materials that you specified in Revit and then add an environmental impact to them. So they did that in collaboration with ThinkStep, the consulting firm, and actually an alum from the Concrete Sustainability Hub. She's the one who kind of did all the LCA work behind it. So the limitation with that, well, there's a couple. One is that obviously you have to have very specific materials defined, and then essentially you go into the Tally plugin and say, this is what this material is, right? And then you kind of do that mapping. And then you have this other issue that it doesn't have a connection to the use phase at all, right? It's just embodied. So you have that also. So it just depends on getting back to this, how flexible can you be in the design process even when you're using BIM? And this is the struggle for us is kind of when you're thinking about how to integrate this into the design process. It becomes as much about trying to think about LCA as it does about what's the design process. And I think for many architects, that's kind of like a philosophical discussion, right? It's like, because we've had some that say, this is a tool I would maybe use before I even sit down at the computer to specify something using BIM. Like maybe by the time that you're going to be entering something into BIM, you already need to have some of these decisions made. And so the short answer is I'm not exactly sure how this would integrate with your using BIM, because we want to do it in a way that best supports decisions. And so you obviously have flexibility in BIM in terms of what materials you're defining, and so we don't know exactly yet how that's going to work out.
And you have level of detail. You do part of what you said, you have level of detail in BIM model. So it could be interesting to link.
Exactly.
And you have EFC in the industry foundation components, and you could have the same categories and have a linkage.
Exactly. So I think there's a lot of opportunity there.
Okay, more questions? Roland, please.
Just a quick comment on input-output notes and then a question. The issue of whether we could use input-output or hybrid analysis came up in the early days of developing environmental product declarations. And the basic reason why we turned against it was that the data just weren't there. The input-output models are too aggregated and the data just aren't good enough. Now it's getting better. We're getting disaggregated input-output models. I think there's still a way to go before you could use it with this sort of application. But then the question. Thanks very much. I take your point entirely that the first few PowerPoints could be for any sector. Here is exactly stuff I've been doing with the microelectronics, for example.
Yes, exactly.
Then when I get to your levels of classification, in the electronics sector, and also increasingly in the food sector, you go to a level 6, which is specific suppliers. Now, I don't know whether that is as... Obviously, it's critical for microelectronics because they're concerned about conflict minerals.
Yes.
And it's critical for the food sector because they're concerned about actually labour practices of specific producers. Is there an analogy in the building sector?
Yeah. The big question we get asked is, can I use a specific EPD?
Okay.
Basically, and so we haven't actually set this up to where you would choose a specific process yet, but I think the feedback we've gotten is that we need to, because particularly, and that's what's kind of nice about this, is that you can be specific about things you want to, and then generic about other things, and there are times when basically you want to say, I want to get credit for using this specific concrete supplier or whatever.
Yeah.
And because, in the US, the lead design standard is basically driving a lot of this, and so that's what's driving a lot of people to generate EPDs in the building sector. And so we think that's going to be a critical component, where basically your next step is basically to just do a very specific one for that reason.
My name is Kashif. I came here from University of Polo to study this. Just arrived today.
Great, thank you.
I want to ask that there is a similar type of process which I have already studied through. It is like material flow analysis and energy flow analysis. It also starts from the embodied phase and then to the use phase and then the demolition phase. But it is called like urban metabolism.
Okay.
I have studied that Dr. John Fernandez books as well for this. Is it come under the same umbrella, or this your work is like different from that? And
Sure. The material flow analysis or urban metabolism, those usually will have like a little bit different scope. It's kind of like, I don't know what your academic background is, but if you're familiar with like control volumes, right, which a lot of people like to use, it's kind of like, where do you draw your control volume? So in material flow analysis, you will draw your control volume around kind of a specific boundary and say, I'm going to track all the things coming in and out, right? A life cycle assessment usually will take a value chain approach, right? And your control volume is around the value chain for this specific thing, which is something that could still be within that urban metabolism boundary, if you will. So it's kind of like it's taking a little bit different approach. Like in mathematics, there's Lagrangian and Eulerian coordinates that you use, whether you're either following a particle in a flow or you're staying at a fixed boundary. And it's kind of a similar type thing with that. So, I think there's nothing to say that these types of approaches couldn't be used in material flow analysis, where you could also just be kind of generic about certain types of flows. And I also do work in material flow analysis and often think about this, because when you're trying to collect data on a lot of those things, it's hard to know, it's hard to get specific details on everything. But you'd like to be able to say, here's what I found with a rough approximation, and then be able to refine that further. So I think the approach could definitely be used in a material flow analysis context. We just haven't done it yet. So. Yeah, sure.
It's more like a comment.
Yeah.
I work as an assessor with BRIAM and with systems.
I see.
System administration.
Mm-hmm.
So I was thinking this more in this way. So I work with architects, and we try to come up with something that is both energy efficient and also it complies with the material range. And I think this is a good way to maybe change the credits of LCA and energy, because we are now I'm struggling to do that with them, because here in Portugal we don't have too many EPDs. Now they are asking for EPDs.
I see.
So, and I also develop EPDs, so I know it's difficult to
Yeah.
there. So I think this is a really good approach, and I think we should come to
Great,
this.
thank you. Yeah. I think one thing that's interesting about the building community, and the LEED standard reflects that. Just in case you're not familiar, that LEED is Leadership for Energy and Environmental Design, something like that. But basically, it's building standards. It's not required in many places, but it's something that people ascribe to. And but the standard is set up such that there are credits for energy efficiency, and then there are separate credits for environmental impact. And the environmental impact just deals with the embodied portion of the building. So, for example, and that's kind of how those worlds are set up, right? Like, usually architects will pay someone else to do the energy analysis, and then the architects focus on the building, right? And this kind of, thinking about them together doesn't usually happen, even though when you come at this from outside and say, so from a life cycle assessment perspective, it's clear you should be focusing on that energy, right? But of course, the materials that you choose and the design decisions that you make influence that, which they know that, right? But the interesting thing about how the standard is set up right now, so there are credits that you can get for using materials that have EPDs, but of course they don't specify right now what that level of EPD has to be, right? You can be a company that's a very high environmental footprint, but if someone uses that with an EPD, then that's fine. And I understand it's an evolutionary approach, right? We want to encourage those, and later on you do that. But the interesting thing, there is also a credit in the version 4 standard for doing a whole building life cycle assessment. But the interesting thing, the whole building life cycle assessment is just for the embodied portion of the building, right? And so you basically calculate a baseline building, and then you just demonstrate that you can get like 10% lower footprint than that, and you're fine. But of course, as anyone who is designing a building knows, often the ones that are the most energy efficient can have a higher embodied footprint, right? So what you would do in that case, if you're going LEED standard, you would just kind of ignore that whole building LCA and just get the energy efficiency points, right? But it would be nice to see in the future some kind of cross-pollination there between thinking about that energy and embodied together. Because for a lot of them, I mean, at least some of the folks that I've spoken to, the best way to get that, to basically say, here's a baseline building, and I've just made very slight modifications to get to 10%. It's essentially just to say I've taken my concrete and then I've used some supplementary cementitious material like fly ash or steel slag or something like that. And because the buildings by mass use so much concrete, that often allows you to get that, but it's harder to do it with other kinds of building materials and still maintain the same energy performance. So I think there's an opportunity there to try and improve that. Yeah.
Or it can go the other way around. I don't know if you know the Centre for Interactive Research on Sustainability at University of British Columbia.
I know.
They went for the lowest embodied environmental impact. In terms of environmental energy performance, it's the worst building in chemistry. They may not tell you that out loud, but I can tell you that for a fact.
Yeah. I mean, it's one of the frustrating things for me is I hear all the time, this is a sustainable building material, no matter what it is, right? And usually they talk about it in the context of just the footprint of that material, right? But if you do it without thinking about that, what that whole building or the whole life cycle environmental impact is, it just seems crazy. But I mean, it seems obvious to us, but most of the time when I go around talking to people in the building industry, like my number one message is just to take that life cycle perspective, right? I don't care what it is that you're talking about, take that life cycle perspective, but people aren't. The other thing I'm sure we all know is that there's lots of claims about green performance, whatever the industry is, and so so the building industry is not immune to those types of claims. So.
Following off that, how do you get on with the materials community? I mean, what's behind that? I went to a meeting of the Materials Research Society probably 5 years ago.
Yeah.
They asked me to do a plenary talk on sustainability.
Yeah.
And they really think that sustainability is a material property, and you look it up in a table. And the idea that it was an emergent property of a system, they couldn't get it.
Yeah.
I mean,
well, but I find the same. I don't have as much interaction with the research community, but definitely these material industries. I mean, so I don't think I mentioned this at the beginning, but the Concrete Sustainability Hub is jointly funded by 2 industry organizations, the Portland Cement Association and basically the Ready Mix Concrete Research and Education Foundation. So we have 2 industry organizations, but they have many members, cement companies and concrete companies. So they're always telling us that the wood industry is making all sorts of claims, and of course, and wood absorbs CO2, which they like to talk about, but they don't talk about at end of life what happens to that CO2, and so that's also important to taking that whole. But a really big push, particularly in British Columbia, is to use cross-laminated timber, right? Which I'm not sure if you've heard about this, but it's basically taking wood and making a composite out of smaller pieces of wood, and they want to build very tall structures with this, which hadn't happened before, and they talk about it as a sustainable building solution. And so the concrete people are always, can't you guys come up with something to tell that's wrong? And I just say that you really just have to take it on a building by building cases and a basis. And the reality, I just haven't seen a lot of information about the energy performance of buildings made with CLT. And so what a lot of people know is that there are many factors that drive energy performance of a building. A lot of it has to do with how tight the building is. And but until you see more of that, it seems like it's hard to make those claims. But they happen anyways, you know, so.
I have a question now.
Sure.
Comment.
Yeah,
okay,
yeah.
I really like your presentation. It's really an interesting topic, and I think it shows in a very, very clear way several things. One of them is that it shows how you can really find out where you need to put your efforts to reduce CSM.
Yeah.
I have a few questions about this, but then there is a parallel message in your talk, which I found very, very convenient to some of my researchers here, because this follows up from discussions I had with them, and this is data is extremely important in LCA, of course, but you didn't focus so much on data, you didn't care about that. And I think the science and sale done, for example, to Vanessa, because the students or the researchers are expecting to find the perfect data. There is no perfect data.
Yeah,
Assume the data is wrong. Because data is wrong. You will never have the data you need, and data change that is very iterative. So we need a lot of data, but we cannot be limited by that. And this is a parallel message. I think that your talk and this approach, focusing a lot in a lot of, you need a lot of information, but not focusing, this is the perfect data.
Sure. Yeah.
So it's really interesting, I think, and it goes very well with this audience, and I think it was very useful for that. Thank you very much.
Good.
Now, going to some difficult questions, or what I think are difficult practical issues, and I would like to know a little bit more from you, is this. From my experience of working with uncertainty, so if you start at a very low specification level, you will have huge variations and huge uncertainty. So this is really a difficult question. So how useful is a tool, for example, if you are in a level of underspecification quite low, so in the beginning of your numbers, and but then you want to make decisions like, should I use the type of wall or the type of insulation or the thickness, and then you have trade-offs between embodied and used, and with huge variations, can you really see the difference, or really you have to go to such a higher level of specification? So that's really my trick.
Sure.
From your experience and what you have done so far, where do you think you can start providing responses to decisions in early phase, which I think is really important?
So I think that it kind of comes back to what I was saying about, it's a little bit philosophical about what is the design process, right? And so I think, we could do an initial calculation here where everything was at level 1, meaning huge range of analysis period, any climate in the country, any size, we could do that calculation. And as you said, it would just be huge. But I think the more we thought about it, it just seems silly that there'd be any architect that says, I don't know where I'm building my building, I don't know what size, it wouldn't really happen, right? And so I think that's why even like with this right here, the range, I don't know what it, like maybe 20% plus or minus, but we kind of feel like this is where a lot of architects are going to start, right? I know the location, I know it's going to be 3 bedrooms, 2 stories, like I already kind of have a client in mind who's gonna do that. So I think you can calculate something with huge uncertainty, but you want to think about it in the context of what are the decisions that you're going to make. And so I think the reality is that there probably will be a lot of things that you will be able to specify, and you can specify those things, but then the things you haven't, that's where you think about it in the context of decisions. The other thing that I haven't really got into here is that we are setting this up to be able to do comparative analyses. And I hinted at that a little bit kind of in this analysis here, where basically you would say, well, I'm going to do a comparison analysis between this insulated concrete forms and wood studs. And so we can do calculations where we use a comparison indicator to basically be able to see how much lower is one than the other. Okay, so I think that's really what we're targeting after, because those are the kind of decisions that you expect one to be making, is those comparisons between the two things. So I think that's ultimately going to end up being your criteria, is basically not just kind of eyeballing this, but quantitatively, can you say how much lower is one than the other in that? And then you might have to do your iteration and specifying things until you get that. And then what's interesting is that you know, your the sensitivity analyses then wouldn't just be based on what's your contribution to variance on the total, but what's your contribution to variance on the difference between those two alternatives. And so I think that's the kind of difference, that's the kind of direction you want to go. Basically saying, even though maybe this wall core influences the whole thing, maybe what you're more interested in is when I narrow it down to these two things, what do I need to specify in order to improve that
You
decision?
use a comparison indicator.
Yes, exactly. But then, like I said, we then calculate is what's the influential parameters on that comparison indicator, which is likely going to be a different number than what's the contribution to variance on the total, which is what we're calculating right now. So I think that's the direction we're going to be heading.
Just a curiosity, because it's very nice to see the values for embodied impacts over there,
Yeah.
which if you compare to Portuguese reality, we have more or less the same.
Yeah.
But
This is more traditional American construction.
It's not applied to Portugal anyway. And also it was interesting to see that you have the embodied impacts and then the really huge variation you have there. Of course, it's so small that it's not so important there, but if they are at the same level, then which is the Portuguese case, then
Exactly. I think the other thing to keep in mind, this is for residential construction, but even a lot of data that I see on commercial construction in the U.S., maybe it's not quite that, but still probably 80% use phase for more conventional. There clearly are much more advanced designs where they're thinking about those things and you can get them closer, but I think that still for just kind of generic architecture, it's going to end up looking like this. So, yeah.
There's another stage in which you could develop this. I mean, there's quite a lot of work now that the energy efficiency in the use phase depends very strongly on who's using it. And that interaction between architectural design and behavior hasn't been developed enough. I can see you could take it that way.
I was talking a little bit about this with Carla about kind of like the human behavior element to it. It's true, like based on our energy models right now, just assume kind of a generic user. And this for me also gets back to kind of the philosophical discussion about what's the purpose of these, because I've even spoken with folks who do these energy models and talk about like basically how important is it that even the energy models track an exact person, right? Because energy models are meant to support these design decisions, but the question is how can you do that? How can you do that in the absence of maybe knowing exactly what kind of behavior the person is going to have? And so I think the opportunity is basically, is there a way to try to incorporate that kind of social science dimension into the design process in a meaningful way? Or should you just take an average then? Basically, if like what should you do if you don't know who the user is? Basically, how do you make those decisions? Comparing, maybe you have an opportunity where you really very much do know that.
There's another way of approaching that, is to say, how would you design it to encourage a particular kind of behavior?
Yeah, absolutely. And then I think what you'd have to do is then have the energy modeling reflect that. But I think you're absolutely right. There's a big opportunity.
Okay, I think we are done and no further questions, I guess. So thank you very much, Jeremy.
Thank you.